Welcome back, everybody. Today we're going to keep playing around with trig sub, this strategy that we saw last time, whereby injecting trig into an integral where it wasn't there before can sometimes allow us to, by using a trig identity, actually rework the way our function looks into a form that we can actually integrate. And so the identity that we were using last time, right, was our kind of Pythagorean theorem identity, cosine squared theta plus sine squared theta equals 1. And the integral we were looking at was this one right here. And our thought was, hey, if we kind of squint a little bit, this a little bit looks like what we have if we kind of if we push the sine squared over, right? This kind of looks like 1 minus sine squared theta, right? Where we have, we got some number minus something squared, well, number minus something squared. So, well, maybe if we do this substitution over here, right, where this 4 is strategically chosen so that when we sub in for x and square things, this 4 becomes 16, matching up with this number over here, which then we can kind of pull things out, and we'll get left with exactly 1 minus sine squared we want to see, right? And at that point, we can then use our identity here and swap that out for cosine squared and continue on our way simplifying, hoping that we'll get to a point where we can integrate. And so at the end of the day yesterday, we talked a little bit about some flexibility that we have in our strategy, that we could also handle things and say if there was a number next to our x squared here, we could do an initial u sub to clean that up a little bit. Today we're going to talk about some more substantial flexibility that we have to use trig identities to help us change the way other types of functions look. We're going to talk about a few of these situations and then put it to work with an example. But the flexibility and the forms of functions that we're able to handle, they're all completely dependent and completely informed by our trig identities. And so let's keep that in mind as we look at this list here. Okay, so the identity that we used last time is right here, right? The 1 minus sine squared theta equals cosine squared theta. And because of that identity, we were able to handle this form that looked like some number, right? Last time it was 16 minus x squared. And the way that we can handle that is by doing this sub, right? Where we want to have this 1 minus sine squared appearing. So we're going to sub in with some scaling of sine, and we just choose that scaling so that when we square it, it matches the number that we see over here. But now another identity that we have, if we just take our cosine squared plus sine squared equals 1, divide everything by cosine squared, right, we get this Pythagorean theorem identity relating tangent and secant. And if we squint our eyes at it, on the left-hand side looks like some number plus something squared. And because of that, we are able to handle forms that look like that, some number plus x squared, through this substitution on the right. Again, the idea is we want to make this left-hand side appear through our substitution. So we'll substitute in some scaling of tangent for x. Again, that scaling just chosen so that when we square it, it matches the number. And finally, if we take this identity in the middle and just take the 1 and subtract it over to the right, we get the identity down here, secant squared theta minus 1 equals tangent squared theta. And thinking along these same lines, this left-hand side is going to allow us to handle forms like this, x squared minus some number, right, since we have something squared minus 1. And the idea is we want to make a secant up here where our x was, and so we can handle that with this substitution, again, with our scaling chosen so that when it gets squared, we match this number and can then pull out that common factor. And so I really want to emphasize that these forms that we're able to deal with and the substitutions we use, they're all completely informed, completely determined by these trig identities. So if you know these identities, well then you can figure out what to do. Right? Everything branches off from these. We also have the added flexibility, as we did with the form we saw last time, that if our x squared also has a number attached to it, well, we can do that, handle that with an initial u sub if we'd like. So for example, we had 9x squared minus 2. We could again try and get this stuff on the left written as something squared. And the way to do that, right, is going to have to be with 3 and then x squared. And then, right, our ultimate goal is to just make this a single variable, right, u squared minus 2. And so we can do that with a u sub u equals 3x. But then, right, we'll need to incorporate the differential there in the u sub. But that's how we can take care of that and make it look like one of the forms here in this list. All right, so without further ado, let's take a look at our example here. So we have an integral, and at this point, pause the video, take some time to work through this and get as far as you can. All right, the first step is going to be kind of looking at our list of forms that we can handle, seeing which one matches the situation. And once we've found that, right, we have our kind of 4 steps to success. We're going to do our substitution. We're going to simplify as much as we can. At some point, hopefully, we should be able to integrate. And then after that, put back in terms of x. Take some time and see how far you can get with this. Okay, well, let's start talking through this. So the first thing to notice is that under the square root, where we're kind of looking to simplify things, this looks like a number plus x squared. And so that's here in the second case here. And so here's our key identity, and we're going to do our kind of trig u sub, letting x be some scaling of tangent. All right, and we need to scale it by 2 so that when we get squared, we match this 4. And taking the derivative here, we see that dx is 2 secant squared theta, d theta. And now we can go ahead and start substituting in. All right, so wherever we see an x, we're going to plug in with what that x equals, 2 tangent theta. So we see that here, and we see that here. And then here, our dx, right, we're going to swap that out with what it equals here, the 2 secant theta squared. Okay, so with that, we have done our first step, and now we have some algebra to work through. Okay, so to start, here just to make things a little bit cleaner, we could slide this 2 secant squared into the numerator. Down here in the denominator, and each of these terms here, this exponent of 2, we can distribute that nicely to the 2 in the tangent. Right, exponents do distribute nicely over multiplication and division. And so distributing that, we're going to get 4 tangent squared in each of these situations. And at this point, right, we now see our plan starting to take shape and pay off. These 4s are matching, and so we can now pull those out as a common factor, still inside that square root. What we're left with is 1 plus tangent squared theta. And here we see exactly that left-hand side from our key identity. This equals secant squared theta. All right, so swapping that in and keeping that all inside of our square root, we now have what's down below here. We're left with just root 4 secant squared theta, and we have some more simplifying to do. You might be wondering why I'm keeping this 2 and 4 around instead of simplifying those. We could definitely simplify at this point, just for, I guess, clarity in seeing what we're up to. I'm just keeping these the same and just working with the square root for now, just as a choice. So we could definitely work with those if we wanted to at this point. Okay, but so anyways, continue on looking at our square root. We have a square root of a product, and so we can break this up as root 4 root secant squared theta. And again, there's some technical assumption under the rug that we're not worrying about that tells us that root secant squared is going to simplify down to just what we would like it to, just secant theta and not absolute value. All right, and the root 4 becomes 2. And at this point, you know, we're happy. Our square root has gone away. At least we don't have that. We have a whole lot of trig to look at, but we can at least be thankful for what we have, which is no more square root. And now let's actually kind of get to work and do some simplifying here. We have everything's multiplied and divided, so we can cancel this 2 and this 2. We can take this 4 in the denominator, slide it out front. It'll stay in the denominator, so I'll have 1/4 constant multiple out there. Let's see what else. We have 2 factors of secant up top and 1 in the bottom, so that'll cancel off with one of those, and we're left with just a secant up top. The tangent squared is hanging out. So at this point, the obvious simplifications have been carried out, and we're now left looking at our function here and wondering how to integrate it. And so staring at this, you know, maybe there's some things we could try. There's a tangent squared in the bottom. Maybe we could think about a u sub at this point. Oh, like maybe a u equals tangent. But I think the issue we're going to run into there is the derivative secant squared of theta is not going to quite gobble things up. We only have one secant up here. And so this doesn't seem to be helpful. Any other ideas as to how we can make progress in computing this integral? If you said writing everything in terms of sines and cosines, then that is a great idea. One of the things we talked about in 7.2, looking at our kind of triggy integrals, is that sometimes if we have tangents and secants in our function, one way to make progress can be to write everything in terms of sines and cosines and hope that what we're left with at the end of the day is something that we can handle. So let's try that out. Let's try writing in terms of sine and cosine. And so to do that, we just need to remember the basic definitions here. Right, secant up top, that's 1 over cosine. And tangent theta is sine over cosine. And so up top, we're going to have this 1 over cosine theta. And in the bottom, sine over cosine is going to be squared. And so we'll have sine squared theta over cosine squared theta, right? Taking that square and distributing it to the numerator and denominator. And so since this fraction's in the bottom, this is going to flip and multiply. And what we'll have is what we see here. All right, so here's our secant theta, and here's our flipped tangent squared. And at this point, there's a little simplification we can do. This cosine can cancel off with one of the cosines up top, and we're left with cosine over sine squared. Any thoughts on how we could try to possibly integrate this function? If you said u sub for this function, then nice work. This is going to work out. Right, the idea here, what's different than the situation just a few moments ago when we had tangent squared on the bottom, is now if we let u be sine theta, the derivative there, cosine theta, is actually exactly hanging out up top. And so a u sub should gobble things up nicely and simplify to a form that we can integrate. All right, so working through that, here's our u and our du. Down at the bottom, this is going to become u squared, and then our cosine theta d theta, that just is going to become du. All right, now what we're left with is looking much more manageable, and in fact we can integrate this, right? We can write 1 over u squared as a power of u. This is u to the minus 2. And so integrating that with the power rule, we're going to add 1 to the exponent. And careful here, negative 2 plus 1 is negative 1. And then we'll divide by that new exponent. And dividing by negative 1 is the same as multiplying by negative 1. And so here's our antiderivative. We finally integrated after all of this work. And here, just writing this a little bit more cleanly, dropping this u to the minus 1 to the denominator with a positive 1 power. This is what we're looking at here for our antiderivative. All right, so that's our third step complete. We've just integrated. Now what's left is putting things back in terms of our original variable, right? And recall the idea here is to use what we know from our original trig sub and triangle. Right, and so here our very original kind of trig u substitution here was where we let x be 2 tangent, and so solving for the tangent here, get x over 2. And recalling through SOHCAHTOA, that tangent is the opposite over adjacent. We can draw a triangle, shows a picture of our angle theta, and we can label the opposite as x and the adjacent as 2. All right, and then if we want to know what this third side is, then we can just use Pythagorean Theorem. All right, and so through Pythagorean Theorem, you know that 2 squared plus x squared is this hypotenuse squared. And so just square rooting both sides, again, through our technical assumption that we're not worrying about, we don't get plus or minus, we'll just get the plus. And we now know all 3 sides of our triangle. And so looking back over here at where we kind of jumped over here, I think we jumped over maybe one step sooner than we should have, because looking at this, you know, where's the trig that's going on? In order to get back to x, we're going to have to back up through both steps that we did, right? Our original integral was in terms of x. We did a substitution to make things in terms of theta. And then we did a u sub to put things in terms of u. And so we need to march back through that one step at a time. So first we'll use our u substitution to replace u with what it is in terms of theta. And that was up here. U was sine theta. And so at this point here, let's swap that out, u for sine theta here. All right, and so now we're in the land of theta, and we can use our original substitution to get us back to x, right? And now that we see sine of theta in our function, we can figure out what that is through our triangle, right? Sine of theta is opposite over hypotenuse. And so for our triangle here, it's going to be x over the root. And so making that substitution here, x over the root, and since that's in the denominator, we can flip and multiply. So the root will come up to the numerator, the x will stay right where it is in the denominator. And here is our final answer, back in terms of our original variable x, simplified as much as we possibly can. And so those right there are the antiderivatives of the function we started with. All right, and so this example gives us a look at how we can use not just our kind of sine-cosine Pythagorean theorem identity, but ones involving tangents and secants as well, to inject trig into our function if it has the right form, and through a whole lot of work, be able to work out that integral. Well, nice work working through that. I just wanted to leave us with one last note for today. A helpful thing to know are the antiderivatives of secant. Just sometimes through this work, this is what we're left with integrating. And this is not a function that we've actually talked about this formula for. There's a way to prove this. There's a way to kind of construct this, but it's not very natural seeming and not very instructive. So I'm just handing this to us saying, hey, if you need to integrate secant theta, here's what that is, so that we can kind of have that on hand if this comes up in some of our work. All right, well, that's it for today. If you have any questions, post those to Piazza, and I'll see you next time.